Okay, we're going to start our second session, our soil water conservation, tillage, and covers. We will have a little bit of a switch in speaker order. We've got Grace Ogden will go next. Dr. DeLaune's flight was canceled last night, so he's driving in from OKC right now, but he will be here in time. So it's going to go Dr. Warren, Grace Ogden, then Dr. DeLaune. But with that, Jason, I don't think you need any introduction to this group. So Jason Warren.
Thanks, Brian. So first I want to say it's really nice to have that first session to listen to some of the scientists and researchers that work on similar things that I do in my extension program. And I'll echo what Brian said, having Andrea and her team working on some of these things in their lab and in the field is awesome, because I learned a lot this morning. And now you're going to get it dumbed down. The reason I'm giving this talk is in today's world, there's a lot of talk about carbon sequestration, regenerative ag, improving soils, increasing organic matter to very high levels, and essentially creating a utopia through land management. And there's a lot of talk about how we can accumulate carbon and how high it can get. And so I'm going to present a little bit of data from the NRCS Soil Survey. One thing that's really nice as a result of a lot of this interest in soil health is that the NRCS has added a lot of things to the soil survey to understand the landscape level variance in soil health parameters, one of which is organic matter. They also put out bulk density data. And so we're going to look at some of that across the state. We're going to kind of go a whirlwind tour across the state and look at organic matter concentrations as percent organic matter, bulk density, and then the cumulative organic carbon accumulate or carbon content in the context of carbon sequestration, aka tons of CO2 equivalent per acre. So this is Texas County. And so what I want you to think about is and I present it in different ways. You have the bulk density is that first number, 1.5 to 1.3. And then you have the average organic matter concentration down from 0 to 3 feet. So that's a 3-foot profile of organic matter. And so how that is the soil survey guys, they go out and they map all these soils, and we can have an argument how accurate they are. I think for the purposes that they map the soils and the complexity of mapping soils, I think the soil survey is very good. I mean, it is a resource that is tremendously valuable to the United States on a continental level. But then when they get these bulk density numbers and organic matter numbers, they go to specific sites and collect data from each horizon within the soil profile. And they may have anywhere from 3 to 10 locations where they've analyzed these soil mapping units or soil series very intensely. And so Sumit Sharma, he did his graduate's degree with me, and his project was looking at soil carbon. And one thing he did is he took this data, and he had GPS located soil sample locations, and he collected soil samples and analyzed it for organic matter and bulk density, and then we compared it to these numbers, and there's no relationship. So that's one thing, is that these numbers are really guidance to the actual organic matter content that soil mapping unit could have in it. But when we went out and sampled it and compared our sampled analysis to these numbers, it was very low in correlation, like an R squared of 0.3 or something. Summit could look up his thesis and tell you exactly. But these are not meant to say that a Groover clay loam is going to have an organic matter content of 2% in the surface 4 inches. In fact, when we analyze, that's what's on most of our research stations out there, when we analyze the organic matter content on those dry land Groover clay loams, we get about 1.4 organic matter. And then when we irrigate it, we might get 4 or 5% organic matter in the top 4 inches. And then when we look at the carbon content in the context of climate change impacts or mitigation, we see numbers that range from 90 to 60 metric tons of CO2 equivalent per acre. And so that's what we have out in the Panhandle. Then we move a couple hundred miles east and we get to Payne County. And here are our numbers. We have 2% organic matter, 0.8% in that Pulaski. The Pulaski is a pretty sandy soil that is in proximity to creeks and whatnot. The Norge is an upland soil, and it's going to be about 2% organic matter, and that jives pretty well. That's what's on a lot of the research station here west of town at the agronomy farm. And then you get into these soils like this granola ashport. A granola is a heavy clay loam to clay, and then the ashport is kind of a bottomland soil. It must be a hodgepodge there and where this was. But this is a soil that's frequently flooded. And so that's really the only way we usually see under rain-fed systems organic matter values that high. So we have 5.8, but then we can also tell, and again, that's 5.8 in the top 4 inches, but then this 3-foot average across the horizons to 3 feet, you only have about 1.6. So what that tells me is that surface organic matter is rapidly diluted as we go down into the profile. And then you end up with about 170 metric tons of CO2 equivalent in that 3-foot profile, and then as little as 67. So what's fascinating is, you know, we're at the bottom end of that scale out there in the Panhandle, but we're still within the scale of what we would see 300 miles east where we have 35 inches of rain versus 15. And we'll talk a little bit about why that is here in a bit. And then you move out over to Ottawa County, over by Miami. Then you get into this verdigris soil. I was kind of surprised because if you ever drive around eastern Oklahoma and see construction sites, particularly if you're not on farms, this verdigris is the stuff that lays out black along the construction sites. This plows up black. It's a really dark clay to silty clay type soil. It can be very productive if managed correctly, but it can be very wet as well. And so that one right there, it tops out on a profile basis as having the highest amount of organic matter. And that is because, again, it's generally wet, it's tight, somewhat poorly drained, and so and then that clay is stabilizing it, similar to what was discussed this morning. And then in the same county, what's crazy is the same county, you can have that Craig soil is based on the soil survey data that we have, that's the lowest organic matter containing profile that we'll see today. And they're all in eastern Oklahoma. And so that's got to do with the age of the soil. That soil is pretty gravelly, so it's not going to have a lot of water holding capacity. However, it is somewhat productive because we'll look at some rangeland productivity values or estimates from the soil survey as well to kind of get a grasp of that as well. And then we go down south to McCurtain County, and we're looking at numbers of 2.5% on the organic matter at the surface, which is what we think we can manage. And then the challenge with McCurtain County is those guys just don't get a lot of love from anybody. And the soil survey is sparsely populated with data from this county. And you'll see that when we look at the rangeland productivity indexes, they only have rangeland productivity indexes for one of these soils. And it is just the way it is. It's based on how they surveyed it in the beginning and then how much data they've had the resources to collect since then. But anyway, I think that 2.5% is probably a surface organic matter concentration, and then they didn't get any analysis on the subsoil. But anyway, we still calculated the math anywhere from 80 to 230 metric tons of CO2. And we won't get into much of that today, but these are very large numbers when we talk about annual accumulations of around 0.4 to half a metric ton. And And in fact, in January, I'll give a talk about the challenges of actually measuring carbon that was alluded to this morning with Andrew's talk. And then you have Stevens County moving back to the west. Again, upwards to almost 3% organic matter, and then as little as a 0.8% organic matter. And then moving up a little ways to Kiowa, 2%, down as little as 0.8% organic matter. And so the reason I wanted to talk about this is these are samples that they collect. They could be collected from cropland, they could be collected from grassland, and they're just a snapshot of what it could be. And if you're interested in looking at soil health and organic matter, the one thing I would say is you could look to these NRCS numbers and say, where do I rank on my organic matter in the top, how many ever inches that you sampled relative to the soil survey. And if you're higher than that, you're probably doing a decent job. The challenge with, one challenge with these data is that we don't we could look up actually where all this data was coming from, because they publish that in their laboratory data warehouse, like the location, but I didn't have time to do that. But one challenge is in Oklahoma, in 1930 you had 20 million acres of cropland, and now we have 6 or less. And we only have, I think, 45 million acres of surface land in Oklahoma, so that means that nearly half the state was cultivated. So we don't know how much these numbers were actually affected by historic cultivation from settlement to 1930, even if they were collected from grassland. And we'll look at some mesonet data that Tyson Auctioner collected here in a minute and kind of discuss that as well, is that we have a landscape that was grossly influenced by production management up until 1930, and we've been putting it back to grass ever since. And we're still doing it today. And so even when you look at those, it's kind of interesting that groover was so high relative to the data I've ever analyzed on cropland. And so they must have had a grassland system that they sampled somewhere. So just a summary of this, we have surface organic matter concentrations that can range from 0.7 to 5.8. And a lot of times, I hear people, even soil scientists, say, oh, well, it's hard to get much above 2%. Well, we can get above 2%. In fact, 2% is a pretty good average on our organic matter. Now, people get confused because organic matter is calculated from organic carbon, and organic carbon is half this number. So essentially, organic matter is calculated by multiplying the organic carbon by 2. And that has to do with some of the stuff that Andrea talked about as far as, how much organic matter or how much carbon is in a gram of organic matter and vice versa. And then the interesting thing is our lowest value is in Ottawa County, an area where we get very productive, pretty high primary productivity levels, but that soil is just low in organic carbon. And then we have some of the highest organic matter values here in Payne County, and it has to do with not just the productivity, but the clay content and all these different things. And then you have the Panhandle out there, and it's actually in intermediate levels of carbon. And then eastern Oklahoma, like I say, can have some of the lowest. Now, when you think about carbon, organic matter, whatever you want to call it, you have to think that organic matter has been deposited there and accumulated over geologic time, right? And so during an ice age, what was our weather like? Anybody want to guess? Cold, yeah. Our weather was more like South or North Dakota during the last ice age and every ice age that came in and out. I mean, you really look. I was out at Woodward doing a soils judging contest for the collegiate soil judging teams, and it's fascinating because those soils out there tell you a lot of stories about what happened over the last 20 million years on this continent, because it sits on the shelf of the high plains. And so there's a lot of wild stuff that's happened over geologic time that is incorporated into the history of these soils and the organic matter levels they have. And then those things influence the productivity, and then those things that influence productivity influence our ability to accumulate carbon now. And so here is just a productivity index. These values were, as best I understand, determined by surveying farmers or actually sampling rangeland on these soils at a few places, and so they stick these numbers in them. These are not, super duper accurate numbers, but they can, again, just like everything in the survey, give us a general understanding of how productive that soil is. And so these, the Conlin, the Groover, and the Ulysses, these are all the fairly flat soils, anywhere from 1,300 to 1,500 pounds of productivity per year. That seems high, but it's droughty out there right now, so maybe on average they do, because these soils can hold a lot of water, and when they fill up, they're very fertile, and so we can grow a lot of things out there, as anybody from out there knows. Then we run over to Ottawa County, and then we bring those numbers up to 7,800 or down as little as 3,700 pounds per acre. And so we've got this nice range of productivity indexes. Like I say, those poor guys down there in McCurtain County, they only have one of their soils classified, and that could be that they don't get love, or it could be that whenever they determined this, most of it was covered by woodland, so they didn't worry about the rangeland productivity. And then we get over to Stevens County, and we're looking at 6,000 down to about 3,800 pounds. And then Kiowa, 2,000 to 4,000 pounds. So we got a lot of variety in the productivity of our soils, just within small areas. Everybody freaking knows that. It's real common. But so how does that productivity then relate to organic matter? Because organic matter accumulation essentially is carbon in minus carbon out is the accumulation, right? So we would think that these soils with high biomass or high primary productivity would have high organic matter, but this figure shows us that that's not the case, right? And it kind of goes to something the last speaker said, is that we don't, within a soil or across soils, you may or may not have a direct relationship between soil health indicators and productivity. And that's because there's a lot of stuff in that profile that influences productivity, from depth, clay content, the depth of clay layer that might restrict root growth, the inherent fertility, the pH. All this stuff goes into making these productivity numbers. And I use the rangeland productivity numbers because if we were to use something like corn, it'd be a disaster, or wheat. But this is meant to say this is the productivity of this soil inherently under rangeland conditions. And I also said half the state been plowed up. And even the NRCS guys can go out and look at a beautiful grassland prairie, on a reservation somewhere and say, oh, this is native grass. And then they dig a pit and they find that it's been plowed. And so this is the best we got as far as inherent productivity of soil, and we see that it's not really related to organic matter. So just a summary of this is we've got a lot of variance in the productivity of soils, and a lot of that variance has to do with where it sits in Oklahoma from an east-west relationship, just simply because of rain. But then within a county, I almost fell. That'd be a disaster. But anyway, within a county, you can have a lot of variance in productivity because of those, depth of shallow bedrock or whatever. And then the fact is that the organic matter content, because it's influenced by not just today's productivity, but historic productivity and the rate of decomposition, then it's not very well related to this inherent productivity from a rangeland standpoint. So then you can look, and this is again a beautiful concept the NRCS is working on. These are values, and they're not a numeric value. They're a relative understanding of the organic matter depletion potential. So these maps are showing differences and a soil's likelihood of being susceptible to decomposition of organic matter. And you see they're all brown to red. That's not good. They're saying that across the state from east to west, the best we can do with our soils is have a moderate potential for organic matter decomposition, with in general it being very high, or a high to moderately high. So, and that has to do with our climate. We're warm. Our soils, how many days out of the year do you think that you would get a 40-degree soil temperature in Tipton? Or how often do you think you get a temperature that's below 40 degrees at 4 inches in Tipton? Any guesses?
Last 5 years or 20 years?
Through the 20 years of Mesonet data. The answer is there are, like 10 days. And then below that, at the next level, there's never a time that soil is below 40 degrees. But even more impressively, in the southern part of Oklahoma, at 4 inches, it seldom gets below 40. Very seldom. In the northern tier counties, you may have 30 days that it's below 40 degrees because we're insulated, right? And that goes to some things that were talked about this morning, is that these soils are 40 degrees is kind of what we use to say below that we're not going to have much microbial activity. And at 40 degrees and above, we'll have some. And so our soils below the near surface, and by that I mean below the top 2 inches, our soils are constantly churning. And we see that if we don't have continuous average or above average inputs of carbon, we won't gain much. And particularly as we look deeper in the profile, like Andrew talked about in California. California is probably the same thing. It's a Mediterranean climate. It never gets that cold, so those soils are always churning. And on top of the fact, if you do things like what Andrea is talking about and start ramping up that microbial community, which is what, it's kind of funny because like no-till, cover crops, talk about increasing microbial activity. Well, what comes with increased microbial activity to a common man like me is that we increase organic matter decomposition. And so if we don't keep feeding the fire, then we're going to lose carbon. Anyway, this is kind of stuff that was covered earlier. As far as there's a lot of stuff that goes into determining how much carbon is in a soil or organic matter. And I alluded to this study. Tyson's done some good work on water dynamics, but he also had the foresight to analyze some soils that he collected from the mesonets for organic matter. He did this back in 2010, back during the last carbon boom that we had. And so I just add these to just provide some perspective. These soil samples were collected across the state at every mesonet location. And just to give you some perspective on what he found versus what the NRCS is telling us, is that you have as little as a 0.2% organic matter in the surface 2 inches versus 6%, and then it declines rapidly as you go down. And so those are numbers well within, in fact, they encompass the entire range of numbers we found from the NRCS. So we have a fairly good understanding of what our organic matter concentrations could be in the surface. And these are all grassland, right? These are all warm season grassland. When you look at the mesonet, that's one thing you always have to understand, is their soil measurements are under perennial warm season grasses. And they might be mowed. What? Oh, I have more time? Oh. Is Paul not here yet? Oh. Well, did you text Grace? Because I'll rip her. But anyway, she works for me. I'm just kidding. So this is what we have. And kind of going to some things that were discussed this morning, this is a graph showing the change in organic matter content at these sites between the installation of the mesonet station and then 2010. So from around 98, then fast forward to 2010, the blue line is the initial soil samples collected, and then the red line is the 2010 samples. And so what you see is at the surface an increase in the organic matter. Well, that makes sense because these mesonettes, have you ever been to a mesonette location or seen a picture? What's around the mesonette site? A fence, right? If there's any possibility of cattle ever being anywhere near the mesonette site, they'll have a fence. And then they periodically mow that. But they don't burn it. They don't do anything but let it grow. And I don't know if anybody is Wes here, Wesley. But I suspect if they're like what I would be, I probably would only mow those locations a couple times a year just from a cost perspective and a time perspective. So this is a perfect system in which we should see accumulations of organic matter if that grass is a healthy stand of growing grass, right? Because we're removing no carbon, like anthropogenically removing no carbon. Cropland, we remove carbon in grain and fiber and forage. Grasslands, we remove carbon through grazing or burning. But this, carbon is not removed.
But in most of them, these are Bermuda type of buffalo type grass around them, not very much tall grass.
Well, like the one out at Lake Carl Blackwell, it's tall grass. And in fact, it's tall grass because it's so god-awfully rough you could hardly mow it. If you're mowing it frequently enough, it'd probably transition. It's Bermuda grass, buffalo grass, or in some cases tall grass. But long and short, you have an increase at the near surface, and then it grades to a decline as you go down to 1 meter. And so when you look at this, Tyson was kind of shocked that on average across the entire state at 60-some locations, or how many ever, there's more than that, there's 90 mesonettes or something? A lot of locations where they have weather data, he found that net there's no change in the carbon content. At the surface, you have an accumulation, but at depth, you have a loss. And this jives with what Andrew was talking about. It jives with some things that I've seen when we were doing carbon work back during this time. And now it could be, and we haven't resampled it, but what was going on in 2010, 11? Was it getting wetter or getting drier?
Dry.
It was starting to get a little dry. And then another thing that Tyson hypothesized is that, maybe we're getting a little warmer. Because he also looked at, so he had 20 years worth of soil climate data is what he calls it. So you have atmospheric climate data, and then you have soil climate data. That includes temperature and moisture at different depths. And that the organic matter content across the state of Oklahoma was most effectively influenced by soil moisture. More soil moisture, on average, over time, results in more organic matter. And that's comparing one mesonette site to all the rest of them. But then temperature, if our soils are warming over geologic time over the last few thousand years, then we could be decomposing organic matter at depth, or we could be priming the soil by mowing that 2 or 3 times a year and depositing fresh organic matter on it. I don't know. That'll be a fun project maybe for Andrea's team to look at some of this in more detail. Is this not going to work?
How many sites were the same?
All of the mesonette sites. So, like I say, there's at least over 77 because there's more than one in every county. And so that's a pretty impressive data set when you look at all the differences in soil type and then the landscape position of those. So then there's one more study I want to talk about. This is a study that Andrea and I worked together. There was a group that bought this quarter of land up in Noble County, and they're going to apply the farming concepts of regenerative ag and organic production So they are going to not spray this or apply any commercial chemicals, and then they're going to no-till it. And so they wanted us, and they looked into all these things about regenerative agriculture, talking about how we can include or accumulate organic matter and offset anthropogenic CO2 emissions by sequestering organic matter in the soil. That is their goal. And so they wanted us to quantify the organic matter in the soil so that they could monitor it over time, and that's a pretty big challenge. And so what we did is we went out there and sampled 19 locations, trying to get a representation of each mapping unit on this farm. And then we also, and so all of this is historically cultivated. And then there was a homestead up here, a corral right there, and this was neglected to be cultivated for whatever reason. As best I can tell, it's never been cultivated, but I didn't study it real close. I'm sure it was. And then these are the soil mapping units we have. We have a Port, Silt Loam, Norge, a West Sum, a Dilworth, a Milan. I'm not familiar with a lot of those, but then we've got a Norge and a Kirkland, which is out here on the agronomy farm. We've got a lot of data on those. Then we got a lot of data on the Port as well. But I put this up because one of the things that these folks wanted to know is, like, how do you manage carbon? How do you monitor it? And the first thing I said is by points, because you can't get an average accumulation of carbon across the field with that many mapping units and that many landscape positions today, and then wait 5 years and analyze the average across, like if you go out there and composite it, because there's too damn much variance. And so what we found back when we were doing a lot of carbon work during the last carbon era, I guess, back from 2008 to 2012, when we were talking about a lot of this before, is that what we figured out is that you have to have a lot of samples from a small area and then monitor that area over time. And then the more locations that you're sampling, the more information you'll have about that field. And then over time, you can start to get an understanding of the average accumulation is kind of the rationale. I don't know. I don't even really know if we're actually right or wrong, but it's just the only thing that makes logical sense that's potentially economically viable. And so what we look at is the range in carbon concentrations, and this is in metric tons per acre, ranges from 83 up to 160. 18 and 19, I point those out because those are Norges, and they're in that grassland area. And you see, 40 to 35 metric tons in the surface, 4 inches. And then the range just in that grassland is 160 to 120 metric tons. And the way this was sampled is we took 5 cores within an area the size of this stage at both of those locations. And we GPSed it, and then we can go back to it. Well, these other blue ones are the Norge that is in the cropland. And I can tell you that when you poke a hole in this, those Norges are not the same. This number 1 had rock, unconsolidated rock, starting at about 18 inches down. And then these grassland Norges did not have that. And that's, if you look in the soil survey and you look at the variance and the characteristics of a Norge mapping unit, it's probably that variable. But anyway, so we have a lot of variance within the cropland from 83 up to 140 metric tons, and then we have a lot of variance in the organic matter in a grassland. And just for the fun of it, I put together these graphs. Here we have a comparison of that grassland to all the cultivated Norge. So if we were to go out and we wanted to say, all right, what's our carbon accumulation potential? if we were to plant all of this back to grass and wait long enough for the carbon to accumulate to its native condition, right? And what we find is that we have a potential of sequestering 31 metric tons of carbon. Now, I have no idea how long that's going to take. The little bit of data we have says that that accumulation rate would be somewhere between 0.2 and 0.8 metric tons per year. And so that's one estimate. And then you look at the highly eroded Norge versus the grassland Norge. So if we wanted to bias this baby really good, we would go out there to a hilltop or actually on the shoulder of a hill, and we take some samples of the cropland, and then we go on the flattest part of the grassland that we could find, and we take some samples, and this would be about what we find. Because that eroded Norge has probably lost a couple feet of soil over time. Because those eroded Norge, this field is fascinating because it had terraces on one part that was mapped as Norge, and then out in the middle of it, they didn't have any terraces on fairly steep shoulders. And you could tell by looking at it, because there's gravel coming up through on the shoulders, that it was heavily eroded. And so you can get an estimate of 59 metric tons of CO2 equivalent. And this is what we did 10 years ago. We did side-by-side comparisons along fence lines. These are not side-by-side fence line comparisons, but you can kind of see where I'm going. And then you have the less eroded Norge versus the grassland. And then you actually get only 4 metric tons, and it's the same kind of deal that we see in Andrew's stuff, is at the surface you get all this beautiful organic matter from that grassland that's very seldom grazed, and then at depth you have that variance that wipes away all this 30 metric ton difference. And then when you look at all the cropland sites versus the grassland sites, you only get 1.3 metric ton difference. And that's because all of the cropland sites, some of those include that Port Silt loam. Where's the Port Silt loam located on the landscape? Anybody know? Down on the bottom. We have data from a soybean field up in around Ponca City. Port Silt loam blows the top off yield of any of these other soils. The Norge is crap. The Bethany, crap. There's all these soils that are in combination with these that are upland soils that have shallow clay layers or shallow bedrock that are just half the yield potential of a Port Silt loam, because a Port Silt loam is silt loam all the way down to 10 feet, and it's layered with organic layers that have been buried over over the last few thousand years, actually, from flood events that flood that port. And so it's a very productive soil, and it's got a lot of organic matter in the profile, and so it wipes away those differences. And here's just another way to look at it, that since we're talking about organic matter and not carbon sequestration per se, we see 2.9% to as little as 1.8% organic matter in that cropland, and then you can bump it to about 5 by planting. This was tall grass. This was like native blue stem and Indian grass and things like that. So we can get a lot of organic matter, and if we plant that back to grass, we'll see what they can do with the regenerative ag management systems that they're implementing on the cropland. And so it'll be a fun project. And that's kind of in the ballpark. One thing about these numbers is I think you can accumulate it. How stable it is Andrea question or an Andrew question. But some of that is that particular organic matter, right? And if you want to alter your organic matter content, just incorporate some residue. Somebody asked about the residue. If you have a clay loam or silty clay loam soil, just jam the probe right through the residue and put that in the bag, and it'll get ground up, and some of it will be analyzed as organic matter. Now, the way I do it is I take my foot and scrape the soil surface to remove the residue, and then shove my probe in the ground. And so these numbers aren't as high, but that includes root mass and any kind of particular organic matter that's incorporated in the soil surface. So like I say, organic matter content in the soil is highly variable. It's both highly variable across the landscape of Oklahoma, as well as within a single field. And the content can change on a large landscape level. And not just in the surface, but in the subsurface. We're seeing losses of carbon, at least when we look at points in time. And I have data like this too, is that what would be nice is to have data from a single location or multitudes of locations under different practices where we analyze it every year at the same sampling date over 20 or 30 years, because then what I think you would see is the temporal variance in whole profile carbon associated with like drought and wet periods, like what you see the Mesonet guys show. But I've just got too many other things to do. Okay, so anyway, and we can increase organic matter through management, but likely not above 3 to 5%. Even above 5%, that 5% number would be the top end of what I would think, and I think you're going to achieve that only by planting grass and mowing it. If you're running cattle on it, it's going to be hard because you're removing some of that. But anyway, there's my contact info. If I've got time for questions, I'll take them. Yes, sir. No, Brian. We're actually talking about having a student do some nitrous emissions monitoring and maybe look at some of that kind of stuff. But
there's actually multiple publications on the organic matter pool of the, or not organic matter pool, but the organic matter content of the last 20 years on the treatment. So
they've got in the manual, like in the pamphlet, they've got the historic data for organic matter depletion in those plots, and then how like the composted manure treatment kind of leveled that off at a higher level, right?
Yeah.
And then the fertility, where just like was mentioned earlier, where you have soils that are never fertilized, the organic matter level is going to decline versus those that are fertilized and maintained at a productive level.
Yeah.
That's what's in there.
Manure, NPK line, NPK without line, then everything else is shelved out, checked, and feed.
So we've got data for the loss of that carbon from the native grass, and then now those plots have been in no-till for 10 years? Oh, they're not?
That Magruder's not no-till.
Yeah. Anything else? What's that? Ripping? I haven't really looked at that and its impact on the organic matter levels. You know, you can look at soil profiles that have been cultivated, and in general, you have carbon loss. The inherent natural carbon has certainly been lost from the depth of the bottom tillage. And so when we look, and it's crazy because there's a lot of stuff that happens when we cultivate soil and we plow down into the subsoil, and you can see it in that surface will often lose its dark color is one thing that happens. And I'm not certain. Surely a lot of that is organic matter decomposition in place, but then some of it is erosional loss of organic matter along with the lighter particles. So the depth of our tillage is going to influence that soil character to some extent, but I've never studied ripping specifically.
Well, my next question goes to the connection to nitrogen.
Well, like I say, organic matter has a 10-to-1 carbon to nitrogen ratio. So like and that's fairly well balanced, and it'll go up and down a little bit. But as you decompose organic matter, you're going to release nitrogen. And if you try to accumulate organic matter, you're going to bind nitrogen into that material. And the extent of that would have to some extent be influenced by the character of the organic matter and the rate of decomposition as a function of your tillage and everything.
Can we enhance our organic matter by just putting nitrogen out at any time? You got a cost factor there.
Well, And it was alluded to this morning, is productivity drives organic matter. And it's always been kind of a chicken and the egg thing for me. And I had this argument with Bill Ron, and I'll have this argument any day of the week, is that a soil that has got lots of organic matter is productive. Right? And we just like the vertigus, it's got crap tons of organic matter and it's productive. Well, the chicken is the productivity, and the egg is the organic matter. The organic matter can't be there unless a dinosaur fell over and died and accumulated all of it, and that didn't happen. The organic matter's there because of the landscape position and water holding characteristics of that profile that allows that place on earth to be very productive versus that crag soil that's not as productive or has characteristics that prevent or that allow for rapid decomposition. Does that make sense? And
So does like you put out your read, does that find that all together?
well,
Organic matter, doesn't it kind of come from nitrogen?
well, it does in the context that it drives productivity. Without the nitrogen, you can't have productive plant growth. And so that's where we look at the Magruders and we see where we have a balance of fertility that's sufficient to optimize wheat production. We have higher organic matter than when we have fertility or pH deficits. And that's because we have less productivity. And so when we fertilize, we improve productivity, which increases organic matter inputs into the soil, and given that biological decomposition is constant, will accumulate organic matter. But then you have issues, and Andrea's better at talking about this, is if you fertilize, then you might prime the decomposition because you're giving those microbes the resources they need to decompose it.
That's kind of where I'm headed with the conversation. It's almost like we need to fertilize sometimes first to get it done.
Yeah, I wouldn't disagree. I mean, I have been asked questions about, say, cover cropping, and I've got somebody out there with an old worn-out Bermuda grass field on a Renfro clay loam that's eroded down 2 feet, right? And then they're told, oh, I'm going to plant a radish and a blip, blap, blap, and I'm going to rejuvenate this Bermuda grass field. And I say, no. I want you to spend the same amount of money that you're spending on these cover crops into this Bermuda grass field and put down the sufficient nutrients called for by a soil test, and the soil test nutrient application always wins the productivity battle because those soils have P levels of 2, K levels of 100, nitrogen levels of 0. You can't get the cover crop to grow to do what it needs to do because the cover crop, and there's a lot of truth to it, cover crops can recycle nutrients to the surface and make them more available, but they've got to be there, is where you're going. I mean, that's what you're saying. And
That's why I originally asked the first question about ripping.
yeah.
It seems like we're having trouble getting organic matter down deep. It's like we have organic surface matter, but we don't have anything below it. You talk about silting
Yeah.
the soil up off the city. You got layers of organic matter because that's silted in over years and years.
Uh-huh.
So it's like we can't get the organic matter isn't going to naturally go down. You know? That's the help.
Well, and I don't know if this, because if my time is up, you tell me, and we can. Because that's a pretty complicated deal. Because I was at, like I say, out at Woodward, and I was looking at this freaking plow pan and this bottomland soil, and I naturally thought, man, I wonder what would happen if you cultivated it. Well, hell, what happened to it when they cultivated it is they got a plow pan that's hard as crap this deep, and then they stopped planting it to grass. So then the question is could we manage that grass, like let it grow and get healthy, and then run a straight shank ripper through there, and then let those roots penetrate deeper to hold it open, But I don't know, because the general answer to that question is to running that steel through there is going to cause that layer to even get deeper or not really, it's just going to settle back. But that's based on our understanding of what a disc and a moldboard plow and a lister does versus a strength shake ripper. And I've done a lot of ripper work back when I was first coming into Oklahoma in this position, and I never really did see a value to it because our yields were never improved on like cropland. And part of that is because when we ripped it, we were running a parabolic plow with duck feed on it, and we were pulling up clay subsoil, and then we had to disc and cultivate the crap out of it to get it to settle back down. So we recreated the problem, fixing the problem that we caused by the ripper. But anyway, I digress. We can talk at lunch. Well, he's asking good questions.
So this is great. We want to continue these questions and conversations through lunch. On soil physical properties and such. This conversation lines up pretty well when we start talking about plows and soil tests and such. She's going to discuss some of her work with, we'll get it brought up, some of her work with, point that back when you do that,
Say it again.
sweep plows and, well, do we need to bring up Ogden?
All right, looks like they're going to get it set up. Good morning. Hello. Again, my name is Grace Flushy Ogden. I'm a PhD candidate. I work for Dr. Warren. To tell you the truth, I'm really a soil science interloper. Like Dr. Arnold said, I do consider myself more of a weed scientist by training. So a lot of what we're going to talk about today is going to be a little bit more oriented toward weed management. However, I do think you're going to be able to see the value of the soil health in sweep tillage. All right, so if you're not familiar, sweep tillage. It's actually a pretty historic tillage implement. First patented in 1932. It's been around for, almost a century. However, whenever we saw a rise in our no-till acres, this tool kind of fell away. I'm sure plenty of you guys do have experience with it, but whenever I first entered this program, I hadn't really heard of it. So to give you a rundown, similar to this diagram right here, it's just a blade that undercuts our soil surface at about 3 to 6 inches. It can come in a variety of sizes. I'll tell you what we use for research is about 5 foot. They can come, 10 inches to several feet wide. Whatever works for your program is great. The key here of what we're looking for and our benefits of our sweep plow are retaining our crop residue on the soil surface. So whenever we talk about whether to use tillage or not use tillage, whenever I speak to producers at least, the crop residue is the most valuable part that I always hear in my feedback. So that is definitely a benefit of our sweep tillage. In our research, like I said, 5 foot blade, and additionally, we do run a rotary hoe or a chicken picker behind this implement just to flip up some of those bigger weeds. So that's a little bit of the weed science side, right? The blade, the chicken picker, undercutting the soil surface. We are separating our weed stems from our roots in this case. But whenever we think about when to use sweep tillage, we need to be very intentional. Something that has been cited in the literature is that our annual grasses, like our cheatgrass, our rescue grass, our annual bromes, a lot of the time we might even see a higher incidence of them following sweep tillage. If we're going to use it, the intentional purpose should be for perennial grasses and maybe some of our large-seeded broadleafs with those deep tap roots. Essentially, when that blade enters our soil profile, we're going to sit here about 3 to 6 inches and undercut those roots. In our perennial grasses, this is going to separate, 90% or more of those underground resources. But in these annual grasses, you're not going to have the same effect. And a lot of the time, like I said, it will only lead to maybe a higher emergence of them or a higher incidence. So We're mostly using it for our perennial grasses, our broadleaves. There is some instances where people use it for liquid or gas fertilizer application, but again, specific purpose of mostly weed management. So some benefits of no-till, again, we're retaining that crop residue. When we do retain this crop residue, we're generally able to retain more of our soil moisture and in turn retain some of that soil organic matter. Unfortunately today I don't have a lot of results for our organic matter quantification. We had some equipment problems this past semester, but I can tell you a little bit about soil moisture. Additionally, today we're going to talk about aggregate stability. I'll explain more of that in a minute, but just get your mind right for it. I would be remiss too if I did not mention some of the disadvantages of sweep tillage. There is a slight risk for compaction. In most cases, if you're using sweep tillage at the optimum time, when our soil is a little bit drier, you probably will not see a compaction layer. However, if you are tilling in the wet spring, sweep tillage can cause a little bit of smearing, which in turn would lead to a compaction layer. They do have a relatively new implement that you can add on to your sweep plow, a finish line plow. It essentially just has a metal bar on the bottom side of that blade that offset some of those compaction actions that we see when the blade runs through the soil. So again, a finish line plow, if you're concerned about that, you could always look into it. Additionally, I am no stranger to the cost of tillage. I understand that's why so many people do opt for no-till. Labor alone can be a problem with sweep tillage. Although they do come in various sizes, just covering a lot of acres can be difficult. So again, when we think about sweep tillage, I hope you understand, let's be intentional. Let's target, be it a weed or, like I said, a few fertilizer applications. So now you kind of get a gist of what sweep tillage is about. Let's talk about the research we did. We have 3 different studies we're going to talk about today. The first of which is an annual sweep study. We applied sweep once a year over the course of 3 years. That study was located in Perkins, Oklahoma. And then we have another study looking at using sweep tillage once and then monitoring our soil for 2 years after. Basically what we wanted to know was, what if I have a problem and I just want to apply sweep one time? What's that going to do to all the soil organic matter I've built up in my no-till system? And then lastly, we have one more study looking at using sweep multiple times in one fallow season prior to wheat planting. Basically here we're looking at using sweep once, twice, or 3 times and comparing it to no-till, and again quantifying our soil response there. As I mentioned, this first study is in Perkins. The other 2 were able to be conducted right outside of Stillwater at Lake Carl Blackwell and then also at an on-farm site in Wakita. Again, we're using a 5-foot blade. It does make for really pretty pictures, as you can see here. Between our no-till and our sweep-tilled sites, you can see some really nice definition of where we're getting control. So, we're quantifying our soil health measurements. As I mentioned, we're largely going to do that by measuring aggregate stability. Our lab has been able to alter some research methods and transition them into methods that can be used for commercial testing. Glenn Garcia, a cohort out of our lab, was able to do this. Essentially, you could submit a sample to Swaffle, and they're going to process it just like they would for your routine NPK. They're going to oven dry it, grind it, such and such, and we can test it for aggregate stability. So if after today's talk that interests you, we can hook you up with that. Aggregate stability is essentially just separating out our dry aggregates and exposing them to rapid wetting of water. What this does is it's simulating a quantitative slake test. It's similar to a downpour of rain that you might see in Oklahoma and simulating that like high-risk erosion event. Here I have a depiction of what you might observe in some high aggregate stability soils to low aggregate stability soils. Again, just a slake test, that rapid wetting is what we're looking for to see how stable those aggregates are. This is the machine that we use to conduct our aggregate stability test, and it, like I said, it oscillates them, exposes them to the rapid wetting, and then also there's a dissolving agent that's added later on. So Glenn Garcia was also able to quantify some aggregate stability measurements you might expect across different soils in Oklahoma. What I want to highlight here is that even in our no-till systems at a few different locations, LCB stands for Lake Carl Blackwell, we'll talk about that site in a minute, even at no-till or even in no-till sites at LCB, we're seeing relatively low aggregate stability. Personally, I find this to be important whenever I'm considering my research. If this has been the ongoing response for years and years, it helps me put things in perspective. When we think about our perennial systems like our grassland or our forest, we can get aggregate stability as high as 47 to 75%. But again, perennial systems with very little disturbance, we're going to have very different aggregate stability in those cases. Okay, let's talk about what we got. So here I have a table with our tillage treatments on our left. We have our p-values here at the bottom, some different years, and 2 different depths. So most of the differences we're going to see in these treatments will be in the 0 to 2 inch soil depth. Across the board, we just see fewer differences in those lower depths, which is kind of intuitive. Our sweep doesn't run that deep. We didn't run the disc very deep in these treatments either. So the 0 to 2 inch zone is where we see disturbance. So 2020, here we're looking at our site near Stillwater, Oklahoma. What we notice here is no statistical difference among any of our treatments. So in this soil, again, I pointed out on the table before this, we already had low aggregate stability. Well, when exposed to tillage, we don't really see much difference. Okay. Moving to 2021, this is a different site. This is in Wakita. Here we do observe some statistical difference among our tillage treatments. However, what I do want to point out is our sweep and our no-till have similar aggregate stability. So what that tells me is they have similar ability to resist a rapid wetting process. However, our disc does have slightly lower aggregate stability than those 2 treatments. 2022 is an interesting set of data. What this is it's all the same plots that were tilled in 2021 and then left alone for a year. So what we're looking at here is our soil response and our recovery in that year following tillage. And what we see is we're going back similar to baseline. We're recovering. We no longer see statistical differences in those treatments after a year. So what this says to me is if you are considering using tillage as a one-time event to take care of a problematic weed or something similar, you could recover a lot of those no-till type benefits within a year. So that's encouraging. Moving on to our annual sweep. So this is when we ran tillage each summer over the course of 3 years. So tillage was ran 3 times. What we notice here, this data is at the end of those 3 years post-harvest. What we notice here is that our aggregate stability is different for each tillage treatment, similar to what you'd expect. Our no-till treatment does have the highest aggregate stability, sweep tillage is somewhere in between, and disc tillage is lowest, which is, if you think about aggregate stability and what we're doing to the soil, this tracks for what we'd expect. This is in the top 0 to 2 inches of the soil. Again, when we look at the lower subsoil, we don't notice those differences, but kind of to be expected just for the region that we are tilling. Moving into our multiple sweep. These results are really interesting, I think. Essentially, whether you sweep once, twice, 3 times, in the top 0 to 2 inches, it's really no different than no-till. I think I'm going to have to chew through some more data to really get to the bottom of this, but what we do notice here is some subsoil differences. However, they are marginal. So I don't know if maybe we are seeing a little bit of a compaction layer here or some function of that that's influencing our aggregate stability, but interesting. We'll keep monitoring it. I'll have to let you know maybe next year. So moving into gravimetric water. What we looked at here was our water content basically on a foot-by-foot basis from the surface of the soil all the way to 4 foot down. What we do notice is that there is a difference in our no-till and our sweep till when it comes to water. Our sweep till is lumped into the same category as like a disc whenever we think about what we're doing with water. However, this is statistically speaking. When we look at just numeric values, when we go to the next level down, so all the way down to 2 foot, if you notice there's a slight numeric change in our soil water here. This can be due to whenever we run our sweep plow, what we can see is we can see a break in that capillary action. And in a year like 2022, when we had a terrible drought, that break in capillary action can prevent some of that subsoil moisture from reaching the soil surface and transpiring. So again, this is just one little snapshot of data. I would like to chew through this a little bit more before I tell you anything super definitive, but kind of encouraging, definitely interesting to see what's going on the soil surface. To get into yield, this is the most boring part. There were no differences. Across any of the treatments in any of the years, we do not see a tillage effect on our yield. If you look in the literature, this really lines up with what we normally see. Regardless of you disc, sweep, or a no-till system, we don't see that much of an impact on our wheat yield year over year. Certain years, you might see a difference, but on average, it's usually lost in the average. Moving into the multiple sweep, again, no statistical differences. I do want to point out here, though, what I notice is that we don't lose yield to sweep, which if we're thinking about incorporating this into the system and we are worried about that compaction layer or other factors, I think it's important to think about. So we're not losing any yield to sweeping. We'll have to determine with some more data if 2 or 3 times is ideal, but at least 1 time, it's not going to hurt us. So also some other results I didn't present here because I'm going to get tired of saying no statistical difference. We didn't see an effect when we did annual tillage in Perkins either. So a lot of the effects that I'm able to see, again, because of my more weed science trading, has to do with my herbicides. Basing it on your tillage alone, we don't see a difference. However, the differences in the water and the aggregate stability between sweep and no-till were observed, usually in just that top of the 0 to 2 inches of the soil. One thing I do want to point out is some of those differences can be due to our soil chemical and physical properties. So depending on your location and your soil order, we can maybe derive more information from that and determine how likely you are to be at risk for some of these differences. And perhaps the most encouraging piece of information I got from this study is that after 1 year, a lot of our soil recovered. So no aggregate stability differences 1 year after a single application of sweep tillage. So in summary, and I feel like this was a rapid talk, I just went so fast. Our sweep tillage does have the potential to be an effective weed management tool with a marginal soil response. Again, we did look at a few different types, whether you're using it year after year or just one single time. In my opinion, one single time does seem to have some value with a minimal response. I would like to thank the OSU Weed Science team for their help in this project, and it was supported by a RAIN grant through AFREED. And I'm happy to open the floor for discussion. Thank you. I'll also tell you, I'm speaking this afternoon for the specific weeds we targeted with sweep tillage, tumble windmill grass. I know that'll probably excite some of you guys if you have trouble with that, so I guess stay tuned for that.
Question. You guys ready for lunch?
Yeah, that's it.
You might just give it
Yeah,
a little. Sorry about that. Oh, yeah. For those in the back, this is Paul DeLaune. He works with AgriLife, Texas A&M AgriLife. I guess that's how you say it, down in Vernon. And he does a lot of work with conservation systems and cotton and wheat production. And he's going to talk a little bit about making sense of cover crops in a semi-arid environment.
Am I on? Okay. All right, thank you. Glad to be here. I landed in Oklahoma City about 2:15 this morning from DC. So if you feel like taking a nap, so do I. So hopefully I won't put you to sleep. I may fall asleep in my own talk, I don't know. But making sense of cover crops, and there's a lot of different opinions. It makes a lot more sense to some people than it does to others. And I'm just trying to do some research that is trying to make sense of cover crops and where we can use them in a advantageous way, I guess you could say. So we'll go through some scenarios, in a couple different types of systems, mainly cotton and wheat systems that we work with there in North Texas. Okay, where I gotta point this thing. There we go. All right, just let you know where I'm coming from and a lot of the work that I do and where that is located. I'm at the, as Dr. Warren alluded to, I think we've changed our agency name at least 3 or 4 times since I've been there in 15 years, but we're currently Texas A&M AgriLife Research at the Vernon Center. They're about 35 miles south of Altus, Red River. So my region covers the Texas Rolling Plains. You know, talking about conservation ag, in these systems, and we do pretty well in the corn, soybean, wheat across the nation, 65-70% conservation tillage systems. But for cotton acreage, that's down, and then you look at the southern high plains, Great Plains where cotton's grown, it's less than 30% of some type of conservation system agriculture. So how can we improve that? So no-till and cover crops, you know, it seems like we're struggling to have conservation tillage implemented, and then the NRCS Soil Health Initiative came along, and it's like everybody jumped into cover crops. We kind of forgot about tillage. So we have to think about what we're doing here. You know, we're putting the horse before the cart. So cover crops, semi-arid environments, it's not a new concept. A lot of people out in West Texas use that for wind erosion control to protect those cotton seedlings. And of course, some concerns, soil water use, what's the cost? And then you had this new caveat of multi-species mixtures. Do we need to pay for that? What's the advantage of that? Is there an advantage of doing that? And then how do you manage cover crops from the time you plant to terminate? And then you hear, well, it may take years before you see benefits. So how long are you willing to stay in the game to see if you see some of these benefits? So really looking at intensifying cropping systems, and what do we mean by that? But that can be done by crop rotation or cover crops or a combination of that. And what we're really looking at is how we manage those fallow periods. So if you're doing annual wheat, in my region it's annual wheat. You get further west, it's a fallow, longer fallow period that can be 9 to 18 months in length. So how do we manage that? And Dr. Peterson, Gary Peterson up in Colorado, several years ago, and up in the Panhandle, Texas, really looked at that fallow period, which was a 11 to 18th month period, and found that that was not an efficient use of conserving water, just because of wind evaporation, and not having protective ground coverage, and was actually losing a lot. So low precipitation use efficiency and capture. So how do we manage that fallow period? And that's different lengths as you go. So going back to this NRCS Soil Health Initiative, you know, that sparked a lot of interest, right? You had soil health workshops, I think, at the old Oklahoma No-Till Conference, had the soil health gurus there. But they started out with these 5 soil health principles. Armor the soil, minimize disturbance, plant diversity, keeping living year-round, and kind of what piqued interest of producers in my region was livestock integration with the dual-use wheat systems. Well, this was another way maybe you could integrate livestock. Well, a couple years ago, they kind of put the X on that for semi-arid environments. So I'll talk a little bit more about livestock integration, and that's kind of dropped out of the Texas NRCS code for one of the, it's really the 4 principles now rather than 5 soil health principles. So first I'll talk to you a little bit about cotton. So the foreground here, this is cotton that's been in no-till for at that point 4 or 5 years. Then we have cover crop treatments, small grains behind that. But as you can see, continuous cotton system, low residue, you're not building up residue, and not much ground protection. So, you know, what are we really doing there is no-till alone enough, and is it giving you the benefits that you may need to see, okay? So then the different type of cover crops, these are legume cover crops going in for wheat. That would be hairy vetch and Austrian pea would be 2 examples, but that residue degrades very rapidly. This is on the left, your left would be 6 to 8 weeks after termination of that cover crop, and then of course you have about 5 to 6 weeks after cotton emergence there. That does provide some protection, but what's the benefit that you may be getting out of that? And then if you look at crop rotation, how would that impact versus just doing a cover crop? So this is a picture of cotton stalks that are shredded in November, and you can still see the sorghum stalks from the previous year. So that's about 14 months of sorghum residue that's still in the system. And then in this particular treatment, there's also cover crops that have been drilled into that. So again, looking at cover crops versus a good crop rotation, and how does that all play in, and does that make sense to do cover crops when you do have a good residue system? And then with cover crops in cotton, this is a rye that we rolled down, and I always joke that I would like to sell my roller crimper, but every now and then it does work. But we roll down rye in this case, and you can see it provides a good protective mat. Can also be somewhat of a physical barrier to weeds as well. So that's what we're looking for in a low residue system such as cotton, is to provide some protection of some sort, some ground residue, and we achieve that with a small grain cover crop, not a mixture, but this is straight rye, and you can see the patch there. So this was rolled in April, terminated, and then this picture is taken August 31st, and you see the boughs cracking there. So lasting residue in that system. So what's the the benefits of having cover crop residue on some of the soil physical properties? This is down in Lamesa on the sandy loam soil, and this has been in place for 15 years when we took this measurement. So they have no-till with a rye cover crop and then conventional tillage. That red line is conventional tillage, looking at soil penetration resistance. So at that about 4 to 6 inch depth, that's the depth layer, tillage layer. You can see there's not much difference between no-till and conventional till, but then you can see that impact of that plow layer as you get into that about 4 to 6 inch range, and then you go out here with the conventional tillage, whereas where we've had that cover crop, it's very consistent through the top 12 inches of the soil profile. So we've alleviated plow plan, or haven't created a plow plan at least, by going with that no-till with the cover crop. And then you look at infiltration, how well does it capture water and retain water, and this is just infiltration rates there, red being conventional tillage, and then blue being no-till with that rye cover crop. So we increase the infiltration with that. So we're seeing some benefits of that cover crop. A lot of people ask about soil moisture. That's our number one concern. If you're planting cover crop, it's going to use all the soil moisture. That's going to hurt our crop yields going down the road. So this is just one graph I pulled out from early on. You have this line down here. So this is in the fall, November, December, where we bedded or listed the ground, conventional tillage treatment. And it didn't rain all winter, spring. So you can see we tilled out the moisture, and that stayed like that through the spring. All these others are cover crops. But then you get into April, that's in our peak cover crop growth period. And not a rocket scientist to figure this out. If there's something green growing out there, it's probably utilizing water, right? So we do pull down soil moisture, but going back to those improved soil properties, when we do receive a rain, and this is in a rain-fed condition, we can usually recoup that soil moisture that the cover crops had used due to improved soil properties. So this is just tracking yields between different cover crops. We have Austrian pea, we have vetch, wheat, crimson clover, which has not done well, and then a mixture of those. And honestly, we started out with a mixture of 7 or 8 back in 2011. Now we're down to 4 because, process of elimination. Why are we spending money on things that do not germinate or contribute to the mix? But long story short, these spikes are wet years, and in those wet years, that's where we see a boost of having legume cover crops. Now, this system we have not fertilized since inception of the study back in 2011. So the last time this ground probably received fertilizer was in the spring of 2011. We planted cover crops for the first time in fall of 2011, and it's been continuous cotton with no fertilizer since then. The idea, I think Dr. Baumann was still at Vernon at that time, we talked about using legume cover crops to provide nitrogen. That's when nitrogen was about $1 per pound, kind of similar to what we've seen this year. So this was before the Soil Health Initiative when we started this. We're trying to provide nitrogen benefits, but in wet years we do see some benefits. In drier years it's kind of highly variable, but over the long-term average of 10 years of data here, we see very little difference in yields in a rain-fed condition. So some of the warm and fuzzy soil health stuff, if you're into that, this is mycorrhizal fungi colonization on the roots. Higher with legume species, followed by a mixture, and then the no cover crop, and then conventional tillage. So there are some benefits on some of those microbial properties. Then follow up some of what Dr. Warren talked about, organic carbon. This is using data from the plots. A hydrologist or our modeler plug this into a model. This is the red would be small grain cover crop versus no cover crop. This is irrigated. This would be dry land conditions, but see a trend of increasing soil carbon with that cover crop. The interesting thing, their model kind of showed a plateau of organic carbon with time for that dry land system. Anyway, we've seen a small increase in really the top 4 inches of the soil profile with cover crops. So kind of building upon what Grace talked about, we've seen some issues in our no-till cotton. So over the years, and a couple years ago, we started seeing some of this windmill grass pop into, I think this is conventional till before we tilled it, but in our conventional till and our no-till. So, and then poor stands as well in these plots, and you can see this is a mixture cover crop dominated by rye, but you see decent stands there, but no windmill grass. So then we went to the pivot. We have the same treatments under pivot irrigation, and this would be a no-till treatment with no cover crop. That's a conventional till treatment. So we started seeing this invasion of windmill grass where we were doing no-till. So we're like, well, is cover crops doing anything to this? So this is a mixture cover crop dominated by rye, and then that would be conventional till, and then it's hard to see, but if you look, you start seeing the clumps of the windmill grass, and that'd be a no-till without the cover crop. So one thing we're noticing is where we did have a cover crop to provide competition, and we were out-competing, or we did not see the windmill grass and the cover crop plots. So that was encouraging, and we started quantifying that last fall, as a matter of fact. So you fast forward a year, and this is harvest this year. As we're coming up, guess which plot that is? That'd be a no-till without a cover crop plot. And then this would be conventional till, and that is the cover crop treatment as well. But this past year, it just really took off in the last 2 or 3 years, the windmill grass encroachment. So this year, after harvest, we took a sweep plow to it, and what we were seeing infringement on the borders of our cover crop plots. So I said, well, let's just till all of it after 10 years, and then we'll look at soil organic carbon and some other soil properties and see what the impact of doing a one-time tillage pass to control windmill grass. But something we've noticed under our irrigation particularly.
What do you use for your burn down?
Burn down, we've used about everything you can think of, and we sprayed just about everything you think of, but typically burn down, like for this past year, we used 43 ounce Liberty because we couldn't get Roundup this year. We have a hard time getting that, and then in the past we've used paraquat as well, up to a quart or 48 ounces. Now, Dr. Ballman told me in the past they've used 64 ounces Roundup, 2 shots of that, and have had decent control. So we have not tried that. But yeah, this past year is 43 ounce Liberty, and then came back with a quart of glyphosate right at planting as well.
You don't think your windmill cover grass is resistant yet?
Well, I mean, it's definitely resistant because we're not killing it with anything. So, I mean, herbicide-wise, and we've used the clethodims, the fusillades, those things as well, and we just haven't had any control. It gets worse every year. So, we put out the pre-emerges as well, caparals. Anyway, just not seeing reprowl. So, a whole array of different pre-emerge, post-emerge herbicides, and it just keeps getting worse and worse each and every year. So switch to wheat systems a little bit, talking about conservation tillage and grazing. Grazing is one place I thought, well, cover crops could use. Then the question becomes, well, is that a cover crop or is that a forage crop? Who's defining that? So there were concerns about grazing no-till. That's long ago. Are you going to compact those systems? But we knew these no-till producers were going to be the most progressive. We're also going to be the ones who were interested in cover crops. So we were planting warm season cover crops between annual wheat systems in the summer and see what impact that would have. Now, some work we've done with graze out versus graze grain. In the summer, following right after graze out conditions, we saw decreased infiltration, higher runoff, but that effect would always go away by the time we got back to the fall and by planting. So it kind of mellowed out over the summer, and we never could see any lasting impacts in the fall due to grazing on no-till, and no impact on bulk density. I think Dr. Warren has seen much of the same thing. So the idea, and this is starting back right after the Soil Health Initiative 2013, 2014, is planting that multi-species mix and then drilling that and then grazing that. Flash grazing was the big thing at the time. High intensity, high stalking rate for a very short duration of time, and then terminate that and plant wheat into that. So looking at soil water conditions under here, these top two lines would be cover crop, no cover crop treatments. The red line would be conventional tillage, and then those bottom lines are where we had a cover crop. So once again, cover crops are using water, but here we are at wheat planting, and everything's very similar. If you look at just the surface, the top 2 inches, and we tilled in August, and then anticipation ahead of planting, and then we received a rain, but we kind of tilled that moisture out with conventional tillage. And whether it had a cover crop or no cover crop, our no-till had much better moisture conditions in that planting depth. So here we're not necessarily seeing a benefit of cover crops over a good no-till system with residue, but superior over conventional tillage, just extending our planting window by capturing, retaining water in that top. So real briefly on this slide, aggregates, that's done by, we see an increase in our macro aggregates and kind of what Grace was talking about, stability with our cover crop treatments in our no-till as well. So doing some rainfall simulations on the cover crop versus conventional till, and then no-till without a cover crop. And what we've seen, infiltration is very similar among all no-till treatments. Again, cover crops did not enhance that infiltration over no-till without a cover crop. And this is in a wheat system again. But again, you see the effects of conventional tillage decreasing infiltration versus your no-till system. And then erosion, same story. Erosion rates really go amplify under conventional tillage, but again, no difference whether it's flash grazed covers, no grazed covers, or no covers at all. And I should tell you, if flash grazing was really, it'd be like an average of 15 to 20 cow-calf pairs on 1 acre for a 24-hour period is the way we were doing this back in those days. Some things about duration of cover crops, cover crop termination timing, and these are some microbial numbers, but these are pairs. So you have cowpea cover versus cowpea double crop harvested for grain, mung bean cover versus mung bean grain, and then a mixed cover crop versus a early versus a late termination, and then this last one is a hay cover crop. And the reason I want to show this kind of leads you into our grazing thoughts, or kind of where we want to go with grazing. So we're removing the residue, and the idea is, well, you have to leave that residue out there to have any benefits. So you have to really be careful on how you graze that. So if we're letting that grow throughout the season and wait until it's hit reproductive stage, getting into maturing, and then remove that residue, there's a lot of stuff going on below ground as well. But looking at microbial biomass, the longer you have living root, kind of seem beneficial, but removing that residue didn't affect microbial biomass, bacterial biomass, and then this is active carbon pools. So this is the hay, and then this is that mix that was terminated and left in the field. So this would be our wheat control down here where it's summer fallow, but by removing that residue, we weren't hurting some of these soil health parameters. So the idea, well, if we're not hurting that by removing the residue, can we remove that with cattle rather than using it as hay? All right, so wheat yields, just real briefly, but this would be that mixed hay versus leaving the residue out there versus the control, but very similar across the board. The blue would be a wet year. The orangish color there would be a drier year, but seeing very little differences among these cover crops and versus a fallow period. So lastly, I want to talk a little bit about livestock integration, and here's what the Texas 340 cover crop code currently states. It says it must be understood that any grazing benefits come secondary to the primary purpose of improving the condition of the soil. These guidelines apply to all cover crops. Any grazing that will take place cannot jeopardize in any way those soil health benefits. So I can live with that. That makes sense. We don't want to defeat the purpose of cover crops. We've had some producers in our area plant cover crops, and they treat it like it's a graze out wheat system and keep it hammered and graze it down. But they also said in semi-arid environments, it should be recognized that in most years the cover crop will not provide enough extra biomass to meet the intended purpose of the practice, that'd be cover crop practice, and allow for forage to be harvested by livestock. So really, this new code for our region, they really, discouraging grazing of cover crops just due to the lack of biomass. So that led to questions of, well, what's the frequency, what's the duration, density? I learned that I'm definitely not an animal scientist when I sat in the room and started talking about these terms, the stalking density, rates, and durations, and I knew nothing about that, but trying to come down with a system that we could utilize cattle on these systems. So we have some current projects where we are looking at different grazing durations, different densities. Is that a lot continuous, or is that flash grazing, or do you do intermittent heavy grazing, pull them off and let that cover crop recover? Another thing we do is a low and high seeding rate, and we did a mixture at 25 and 50 pounds per acre, and what we've seen cover crops across the board is that we can get by with a lot lower seeding rates than what may be recommended. A lot of times you see a full, like for instance wheat, if you're planting wheat for grain, 60 pounds per acre, a recommendation for cover crop may be 60 to 90 pounds. We do very well with 30 pounds and produce as much biomass at those lower seeding rates as we do with the higher seeding rates. We saw the same thing here, and this was 2020 and then 21 and then 22 has been very similar for us as well. This was a dry summer, very little biomass, but it did provide something that we could graze that year. So we have basically 8 1-acre strips of cover crops in a field, and just turn 40 cow-calf pairs in that field, let them graze for about 5 to 6 days. Question is, well, how long are you going down? Well, for this particular study, I pretty much let them graze it down to the ground, and then we came back, terminated that, and you can see the residue that we left behind from the cover crops. We left stubble height, and talking with the NRCS, the point is, well, that we have provided stability to the soil on the surface. We're not losing anything through wind or water erosion, and that gives us protection. So that's in debate now, and that's what we're working on. We have 3 or 4 different projects doing that. So this was from this past year. This was August 4th, 2022. That was a multi-species mix, and by this time, the only thing surviving out there was a sorghum Sudan grass, hay grazer, cowpeas, mung beans, even pearl millet. They all bit the dust, but that hung on. So we received about 4.5 inches of rain in August. So this was 6 weeks later, and we had an explosion. So we had written off grazing for this year, but then we're like, well, what are we going to do with all this biomass that we have out there now? So we threw up some wire and we turned some cattle in there. But point is that it can look pretty crappy at times, but you have to remember there's other things that are going on below ground. And this is a picture of pearl millet. We did this a few years ago, but that pearl millet plant's probably about 3 foot tall. We didn't water it very well, didn't keep an eye on it, but it persisted, and this is in about 60 days of growth, and the root mass is, I think it's 72 inches in length. So it's, you think about that, what's going on below ground. So it looks bad above ground, but there's a lot of root biomass, a lot of channels, infiltration, carbon sequestration potential that may be occurring below ground as well. So one thing about weed control in these wheat systems using cover crop, we have this grass, panicum grass. It's very persistent. It's easy to kill with a herbicide Roundup or something, but it seems like every time it rains, there's a new flush of it, and here it comes. But this is where we had that cover crop this summer during grazing, but you can see it down the lines. This is a no cover crop treatment versus where we had that cover crop, and then you look within that cover crop and you can see the spaces in between, but we're not seeing that, that annual grass that we have issues with in those. So we have competition in that system as well that we provided, and it does seem to be providing some weed control for that annual weedy grass that we have. And then on that same field, we did have the old pesky windmill grass make an appearance. So we have 21 acre plots, and then we have several more down here, but this isn't the scale, but this is just to show you. So where we have this issue are the green strips. Those green strips are where we converted to a perennial grass system. So we planted summer dormant tall fescue. Actually, we planted Chisholm fescue in there fall of 2020. So just trying to get fescue established, not being able to spray that. But it's interesting how in those 4 1-acre strips, that's the only place in the field where windmill grass has made an appearance. So reduced herbicide usage, but also just not the competition there. Fescue kind of off to a rough start, but we had to go in on some of these and actually till, and I replanted fescue just this fall. So again, some weed control benefits of cover crops, but also just in a no-till, good no-till wheat system. So lastly, managing long fallow periods. So we have some producers looking at, rather than an annual cropping system, looking at a cotton wheat fallow system. So by going a cotton wheat fallow system, you go cotton, wheat right after cotton, and then you're going to have May harvest until the next May when you come back in with cotton. So the question is, what do you do with that year-long fallow period? So we're looking at planting cover crops and then using that as a forage crop as well. So we have 6 20 to 25 acre paddocks where we are planting either a warm season cover crop that will graze down and then come back with a cool season cover crop and graze again, or waiting until August and doing August, September, and planting a warm, cool season mixture, and then being able to graze that, and then going back into cotton. And then some other studies we're looking at, well, is there a place for perennials in these systems as well? So in conclusion, I don't know if I made sense today, but kind of some places we've seen where maybe some benefits of cover crops, and maybe where it does make a little bit more sense than it would other places. But whenever you have a continuous low residue cropping system, in our case, that'd be continuous cotton on cotton on cotton. Cover crops are an ideal candidate there. And they provide protection from wind and water erosion, and they improve some of the soil function in our soil. And then crop rotation or high residue cropping systems can potentially provide some of these same benefits as doing a cover crop. So a good crop rotation and a good cropping system can provide you those same benefits. Cover crops can provide, I guess I got myself on a timer, it's faster than I am. Cover crops can provide supplemental or alternative grazing options. You know, again, does that mean, does it become a forage crop? But we're really trying to see how we can fit grazing in to make that more palatable to our producers. So replacing fallow periods for cover crops can provide competition to undesirable species, and we've seen that and provide some level of weed control, and at the same time provide soil function benefits. So low residue systems, long fallow periods, when you can incorporate grazing and get benefits out of that, those are some ways that we've been able to try to make some a little bit more sense out of using cover crops in our cropping systems. So with that, thanks for having me today, and I'll be glad to entertain any questions.
Question for Dr. Laune.
Average planting date for cotton. In dry land, it's usually within 2 weeks of June 1st, either side, and for irrigated, anywhere from about May 10th through mid-June. But we shoot for a little bit earlier in May under irrigated conditions.
What cover crop mixes actually became a problem in your cotton crop?
What cover crops have become an issue in our cotton crops? We haven't had any issues. We haven't had any cover crops that have become a weed. I've heard some talk about a concern for hairy vetch, for instance, but we use a 2,4-D or dicamba product to burn that down and get a good kill on that, and we do it during flowering before it starts making a seed. But we've used straight paraquat or glyphosate on hairy vetch or peas, and that will not do the job, and that will linger around. And as I think more, we've had issues with radishes. When we planted radishes, we can't get them to grow when we want them to, but if they make seed, they'll pop up all year long. Yeah.
All
All right.
Appreciate it, Paul. Thank you.
Thank you.